Good. So today I'm going to be talking about the Renormalization Group, unless you have questions, in which case I could start by trying to answer questions.
I have one question, and I think I'm going to get shut down pretty quickly, but is there any chance that next semester's class might start maybe an hour and a half earlier? If it's something you really don't want to do, or if the class doesn't like it, I'm fine. It's just, I thought I'd ask.
I tell you what, why don't those of you who feel that an earlier time would be better, send me an email.
I know you come in.
The convenient thing about this time is that there are people who work at Sandia or the Air Force Research Lab who can't come an hour and a half earlier. And then the other thing is it might conflict with other classes, and this room might not be available or the other room. In any event, let me just, since you brought up that issue, and by the way, if there are more of you who feel that way, then let me know, because maybe I could get up extra early. So let me mention first of all that you can register now for 524. Presently it's Monday, Wednesday, and again 5:30. It's certainly early enough to change the time, but I don't know whether another time is available. I'm also teaching what I can call is 467 light. That's a one-hour seminar on topics in mathematical physics, and these are things that I've partly discussed in 523. In other words, group theory, tensors, general relativity, probability and statistics, and so forth. Path integrals, well, we've just done path integrals in this course, but although because of reasons because I wanted to try to finish as much material as possible this semester, I skipped some stuff in the path integral chapter. Okay, anyway, and this one is, presently it's Tuesdays at 5:30. And there was at least one student who wanted it at that time because he had a job, or has a job. Okay, so first now we're going to be talking about the Renormalization Group. There are two things wrong with this label. One is that renormalization has too many syllables, and another is that renormalization group isn't a group, but this is what people call it, so I guess I'll continue. Now, as you know, quantum field theory is divergent. And the reason it's divergent, presumably, is that it treats particles as point objects, and in particular, the commutation relations, for example, between phi of x and t and conjugate momentum at y of t are I delta cubed of x minus y. This delta cubed is asking for trouble. string theory has the great advantage of talking about extended objects. By the way, Dirac, back in the 1960s, which is 70 years ago, was talking about extended objects. And in fact, one of the things in one of his early, possibly his first paper on that subject, published in Proceedings of the Royal Society in London, is he points out that in order to have an action principle that works properly, his formulation has to be invariant under changes of parameters, which people call reparametrization invariance, which again has too many syllables for me to pronounce reliably. And that's one of the key features of string theory, namely that it's invariant under changes of coordinates. Of course, that's also a feature of general relativity, that you can change coordinates in an arbitrary way and the theory has to remain the same. Okay. Now, because of these divergences, people invented, and the people actually are Schwinger, Feynman, and Tominaga, won the Nobel Prize in about 63 or 64 for their work, introduced ordinary renormalization. And this works presumably because the underlying theory is finite, as it must be, because physics is finite. And so the problem with the divergences in quantum field theory is the theory's wrong, not that there's something wrong with the world. Well, there are things wrong with the world. But actually, there's been great progress today. In Sweden, the two sides in Yemen agreed to open the port of, I think it's called Data or something like that. Anyway, there are millions of people starving in Yemen because of the aggression by Saudi Arabia and the UAE. And thousands of children have starved to death already, possibly 10,000. And but once if the port really does open and food gets in, then millions will be spared. If not, millions could starve to death. It's like a new Holocaust, open air Holocaust. Anyway, what one does in renormalization is one says, well, these parameters in the theory, the charge, we're going to label the charge that occurs on the Lagrangian with a 0, and we're going to say that's the finite charge plus minus a counter term, and the mass that appears in the action is going to be the physical mass minus delta m. And there's another thing, some scale parameter called z, and I guess one can call this as z minus delta z or something equivalent. In any event, what one does then is compute. One replaces the E0, M0, and Z0 by these differences, expands the Lagrangian, and then uses these things as counter terms to cancel the infinities as they occur, order by order in perturbation theory. And what Feynman and Schwinger and Tominaga showed was that this thing works to all orders in quantum electrodynamics and in various other renormalizable theories. What I'm going to do first today is talk about interpolation and then get to the essence of the renormalization group. This is described, by the way, in chapter 11 of Weinberg, and 12. Another approach is to notice that because the underlying physics is finite and the true theory is finite, if we compute a scattering amplitude at two different momenta, then the difference between the two scattering amplitudes often is finite. And that's what I want to show you first today. So let's consider this Lagrangian that I've used a number of times. It's sort of a standard, simplest theory. If one computes, in fact, you got one of the homework problems was to compute scattering in this theory to first order, to lowest order. The theory to second order is G, which is the first order term, minus G squared over 16 pi squared, integral 0 to infinity k cubed dk, integral 0 to 1 dx, and then a bunch of terms, 1 over k squared plus m squared minus sx 1 minus x squared plus 1 over, and it's the same thing with s replaced by t, so it's k squared plus m squared minus tx 1 minus x squared plus 1 over k squared plus m squared minus ux 1 minus x squared. Let me just say what went into this derivation, which is done by Weinberg in, well, I don't know, he skipped a great many steps. The steps basically are you use the Feynman rules to compute the diagram to the scattering process to second order in G, and what you've got is the S amplitude looks like this. I actually showed you this last time. The T amplitude looks like that. The U amplitude looks like that also. So this is 1, 2, 1 prime, 2 prime. This is 1, 1. This is 1, 2. Actually, no. This is a better way of writing that. And in fact, I shouldn't have written any of them this way. There's a better way of writing all three. So, so 1, 2, this is the S amplitude. And then for T, we can also, oops. So these are always 1, 2. And then this can be 1 prime, 2 prime, and this can be 2 prime, 1 prime. So this is T, and that's U. These S, T, and U are variables that Mandelstam introduced. S is equal to minus P1 plus P2 squared. T is equal to minus P1 minus P1 prime squared, and U is minus P1 minus P2 prime squared. Okay, so one writes these, and these involve loop integrations. That is to say, you have to integrate over a full momentum K, and Actually, I now notice that I left out the I epsilons. I'm so used to leaving them out in tree level diagrams that, oh, but this is after, okay, there's a reason why there are no I epsilons. So the first thing you do is you write these down, and you have an integral that is logarithmically divergent. Logarithmically divergent because you have 4 powers of k in the denominator, 4 powers of k in the numerator, so it's a log divergence. Like integral dx over x is log x, and that integral from 0 to infinity diverges, actually at both ends, but in particular at the high end is what's important here. The next thing that you do is this term here has 2 propagators in it, and the 2 propagators aren't easily dealt with because obviously this is a k squared plus m squared. It's a given momentum squared and an m squared, and this other momentum squared plus m squared. And there's a Feynman trick, which I didn't write this down in my notes, but it's something like this. 1 over AB is integral 0 to 1 dx of ax plus b1 minus x, or is it x1 minus x? This is just from memory, and it's not very good memory because I didn't write it down. Anyway, there's a Feynman trick that's something like this. It's an exact identity, and somebody want to Google Feynman trick and correct this maybe. Anyway, the next thing you do is you apply this Feynman trick so that you can write the 2 propagators as an integral over x of 1 propagator squared. And that gets you to this form. Then you want to avoid the I epsilon poles. So the K0 integration, by the way, in 524 I'll do this in detail. Okay. I wasn't going to do this here today. So instead of integrating on K0, you integrate from minus infinity to plus infinity. You go up the imaginary axis in the K0 plane. So the I epsilon poles, I think actually they're here and here. Well, but they might be there and there. Right now I don't even remember where they are. But the 2 poles, well, it's obvious where they are. They're here and there because you avoid them by adding a ghost contour there and changing to this. That's called a Wick rotation. And then you're integrating over Euclidean k squared, and this is Euclidean k squared. So just k1's, and in fact you basically say I k0 is k1 or this, and so then you're integrating just over real variables there. Actually, I called it k0. Okay. Anyway, that's what one has, and these tricks make these things mathematically doable, but it's still logarithmically divergent. Now, the nice thing is that if you subtract, if you write A, this is of course A of ST and U, if you write A of ST and U as, or rather minus, the difference between that and A of S0, T0, U0, so you compute this amplitude in 2 different sets of momenta, or 2 different sets of Manstein variables, take the difference. Well, the difference is actually a convergent integral, and it is minus g squared over 16 pi squared integral 0 to infinity k cubed dk, 0 to 1 dx. And then what you've got is you can write this as an integral from S0 to S of the derivative of that with respect to S. And then it's 2x 1 minus x over, and now it's k cubed, k squared plus m squared minus s prime x 1 minus x. But now this is cubed, and so the k integration converges. And then you have plus the same thing for t prime, plus the same thing for u prime. So you have the integrals of 3 derivatives from S0 to S, from T0 to T, from U0 to U. These are finite integrals, and when you do them, what you get is A minus A0 is, I'll put in 2 steps, minus g squared over 32 pi squared, integral 0 to 1 x, 1 minus x dx. And then integral S0 to S ds prime over m squared minus s prime x, 1 minus x, and then plus, again, t prime, u prime terms. I've done the k cubed integration is, once it's finite, it's an elementary integral. And bingo, you get this as an answer. And then, once it's in this stage, you can do the x integration. And what you get then is minus g squared over 32 pi squared, integral 0 to 1 dx. And now you have a log term, natural log. It is a natural log, of course. M squared minus S0 x 1 minus x over M squared minus S x 1 minus x. Again, and then plus t prime u prime terms. And so these integrals are no longer elementary, but of course they're finite. So because the underlying, because the quantum field theory is kind of right, it's able to compute the differences of scattering amplitudes in many cases as finite integrals. I think it's an open question how general this is. In other words, in how many theories and to what order in the coupling constant can you take the difference of the same amplitude at 2 different momenta and get something that's finite? I don't know the answer to that, and I think it's an open question, but because I did ask one of the world's experts, and he said he didn't know. So if we set S0 equal to T0 equal to U0 equal to minus 4 mu squared over 3, we get the result that Weinberg quotes. Okay. Now, the next step is the renormalization group in quantum field theory. And the idea is, there are 2 things here in this idea. The first is to say, well, let's go back to the original amplitude. The original amplitude, the lowest order is g, and then there's all this other stuff. So the idea is to call this A0, which is equivalently it's g, to say that to identify g with A0, which is A of S0, T0, U0. And so that, once we identify G with this value, we see that the coupling constant isn't really a constant, it's something that depends upon the values of the Mandelstam parameters that we chose in this A0. So that's basically the first step, and we call this G sub mu. This is called the running coupling constant, and the mu here is defined in this particular case by this relation. And so once we've done that, we can write the amplitude A of ST in mu as the running coupling constant G sub mu minus G squared over 32 pi squared equals 0 to 1 dx. And this is then log of this ratio. It turns out to be 1 plus mu over m squared x 1 minus x over 1 minus s s over m squared x 1 minus x plus tu terms. And so so this is basically the first step in the renormalization group program. And it's a very simple idea. The second step was, and these are due to Callan and Zemancic. Callan being a professor at Princeton, and I think he was a postdoc at Harvard at the time, and Zemancic is a German theoretical physicist who, I think he's been, he's at the University, he's been at the University of Chicago a lot, he may have passed away. Anyway, this mu is called the sliding scale, and what Callan and Zemancic noticed was that the mu here is just the value, the renormalization point that we chose arbitrarily. That is to say, arbitrarily we say, well, S0 equal to T0 equal to U0 equal to minus 4 mu squared over 3. And we didn't even say what mu squared was. So the point is that this physical amplitude can't depend upon mu. And so that's the basic Callan-Zemancic equation. And if we now write the right-hand side of this, it's partial G mu, partial mu. Well, let me just do that differentiation rather than writing it down a couple of times. It's 3G squared over 32 pi squared, integral 0 to 1 dx, and 2 mu over m squared x 1 minus x divided by 1 plus mu over m squared x 1 minus x. So again, this is not an elementary integral, but on the other hand, things simplify in the high energy limit. And so let's imagine, I mean, we could do, use, maybe Mathematica can do this integral exactly, I don't know. Or maybe some Indian graduate student can do or Chinese graduate student can do the integral. Or some clever person can do the integral. Can you do this integral? All right. Anyway, however, in the limit of mu much greater than m squared, I can do the integral. And so in other words, the equation is 0 is partial G mu, partial mu. And now if we take the limit of mu much greater than m squared, well, this is just an integral 1 over mu. This is just 1 over mu. And consequently, this integral is just, in other words, this whole thing is approximately partial g mu, partial mu. The integral is 2 over mu, so this is minus 3g squared over 16 pi squared mu. And so the equation then is, if we multiply by 0 is this minus that, we multiply both sides by mu, we get mu here, and, or let me actually follow the notes so I don't screw up with a minus sign. We get mu dg du mu, which is defined as beta of g mu, is equal to 3g squared over 16 pi squared. So in other words, it's 3g squared over 16, we just multiply through by mu. Now, remember that when we identified A0 with g mu, what I should have emphasized, let me just emphasize this. The A0 that we're talking about is the experimentally measured amplitude. Of course, you measure cross sections rather amplitude, but you guess what the phase is, or define the phase. In any event, this is finite, so g mu is finite. And g mu and g are also finite, are the same to lowest order. So this is 3g mu squared over 16 pi squared. Well, now this is a differential equation that we all can integrate. And if we do that, what we have is log, we integrate from big M to big E. What we have is an integral from M to E d mu over mu, well, that's obviously log of the ratio. And now what is d mu over mu? Well, this differential equation, you get d mu over mu is 16 pi squared over 3g mu squared. So this is an integral from gm to ge dg mu over beta of g mu, beta being this thing. And so what we've got here is 16 pi squared over 3, integral from gm to ge, sounds like a stock program, dg mu over g mu squared. And that gives us, after you do the integral, 16 pi squared over 3, 1 over g sub m minus 1 over g sub e. And now if you unravel this, you've got log of e over m, two energy scales, is 16 pi squared over 3, 1 over the running coupling constant at energy m, minus 1 over the running coupling constant at energy E. And if you unravel that, what you get is that the running coupling constant at energy E is the running coupling constant at energy M divided by 1 minus 3 G sub M log E over M, and all of that is over 16 pi squared, so this is 1 minus that. Okay. Now this is all for E and M much greater than the mass scale of the theory. I'll put the notes online. Anyway, there's a link in the video. Whoops. And in the beginning of the lecture, I skipped a lot of material, which is just standard renormalization theory that I'm going to do in 524, if enough people register for us to actually teach the course. It's Monday, Wednesday at 5:30. Okay, anyway, so this is the basic idea of the renormalization group. In this case, and in many other cases, in fact, in all ordinary field theories apart from non-abelian gauge theory, it always looks more or less like this. In other words, that as the energy increases, this logarithm increases, this number gets bigger and it approaches 1, so the coupling constant grows as the energy rises. Okay. Now let's look at an actual realistic example, namely quantum electrodynamics. And the first people to notice this were Gelman and Lowe back in 1954. So this was 10 or 15 years before Cahill and Zemansek made it a general concept. And the idea here is that the amplitude, we're talking about one loop scattering of electrons. Of course, the tree level diagram is that, and then you have various one loop diagrams. One is, let's see, that's one diagram, is that, well, there are other diagrams, I'm just, well, you certainly have this. And there are all sorts of other things that can happen. Anyway, you put them together, and what you find is that the amplitude at q squared being the momentum transfer to the first electron, say q is p1 prime minus p1. This is p1, p1 prime. This thing is e squared times 1 plus pi of q squared. Pi of q squared is just a notation that Gelman and Lowe introduced. And what is pi of q squared? Well, to lowest order, this again is after you've done the business with E0 equal to E minus delta E, M0 equal to M minus delta M, and so forth. And then canceled all your infinities. What you get to the one loop order is E squared over 2 pi squared integral 0 to 1 x 1 minus x log 1 plus q squared x 1 minus x over m squared dx. And of course this came again, whenever you see x1 minus x, you know that the Feynman trick has been used. Did you look it up? Do I have it right? It was right? Goodness, okay. Thank you. So once again, when you have something like this, this integral is a hard integral, but it's very simple in the limit of very large q squared. So you let, in the limit q squared much greater than m squared, this mathematically can do this integral. In fact, I checked the notes this afternoon, having Mathematica do it. And what you get then is for q squared equal to mu squared much greater than m squared, what you get is pi of mu squared is equal to approximately e squared. So in other words, you finesse the 1 and you just have log of this structure, and that's an integral that is known. And this is then log of mu over m minus 5 over 6. And we're going to drop the 5 over 6 pretty soon, I think. And so then the amplitude A of q squared is equal to e squared times 1 plus pi of q squared divided by 1 plus pi of mu squared. I guess I should have put in a couple of more equations to make that a little bit clearer. So the idea here is that A of q squared, I guess, minus A of mu squared would be all right, I forget what it is. I skipped a couple of equations. In any event, this is what you come up with. And now, once again, you take the Cahill-Zemansky equation and you say this must be independent of m, independent of mu, and so you write 0 is d by d mu of A of q squared divided by 1 plus pi of q squared, so just to cancel out the part that doesn't have mu in it anyway. And so this is d by d mu of now e sub mu squared. This was a mu, and it's a square, e squared mu. So then you say d by d mu of e mu squared over 1 plus pi of mu squared, where pi of mu squared is this. And you get the equation 0 is, you approximate this a little bit, is d by d mu of e squared, e mu squared times 1 minus pi of mu squared. That's just 1 over 1 plus something small is 1 minus the same thing. And that gives you 0 is 2e mu d mu times 1 minus pi of mu squared minus e mu squared d pi of mu squared d mu. So this is just carrying out the differentiation, and then you find you have 2e mu d mu times 1 minus pi of mu squared minus e mu squared e squared over 6 pi squared mu. And the 6 pi squared mu comes from this equation here. So, in other words, when you do d pi d mu, you just get a 1 over mu. You get basically e squared over 6 pi squared mu. So then one gets the Cahill-Zemansky equation, or one should maybe call it the Gelman-Low equation. Mu d mu, which is beta of e mu. This is just by definition. This is called the beta function. This is then e mu cubed over 12 pi squared. And so it's basically like the same arithmetic as in the previous example. And so now you integrate it from m to e, and you get that this is an integral m to e d mu over mu, which is integral 12 pi squared d e mu over e mu cubed from e sub m to e sub e, and this gives you 6 pi squared 1 over e squared at m minus 1 over e squared at e. you unravel that, in other words, unravel this equation, what you find is that the electric charge at energy E squared is the electric charge at energy M over 1 minus E squared at energy M times a log of E over M divided by 6 I squared. Okay. Now, this has been experimentally verified, and let me just maybe go back to the very beginning of this idea of the renormalization group. What you do is you know that the amplitude is the coupling constant and then plus a one-loop correction. And so this G of mu is the amplitude is the scattering amplitude at some scale of energy, which we were calling mu. Now, the point is, it's the amplitude at that scale of energy, so it's the amplitude in which you can ignore all the quantum corrections, and you just have that as the amplitude. The running coupling constant is the amplitude, the physical amplitude at that energy scale. So when we go back here, we can reinterpret this equation. What does this mean? This means that E is the coupling constant appropriate at energy M, and E sub E is the coupling constant of electrodynamics appropriate at energy E. And what we know is that if we take the limit M going to 0, then E squared sub M, let us say, over 4 pi, this is in natural units, is what we call the Finestructure Constant, and that's 1 over 137.06 roughly, 036. That's been, if you now compute this thing and put in E as 91 JeV, which was the energy of the Large Electron-Positron Collider at CERN, where they did a lot of these very precise measurements, you would then say that E squared 91 JeV over 4 pi should be, this formula would give you 1 over 134.6. But in fact, this calculation just involves the one loop, an exchange of photons, and ignores the fact that you can have charged quarks, charged leptons, and so on and so forth. If you put in all the light charged particles, this changes, and this goes to 1 over 128.87 at 91 JeV. And in fact, this has been measured and verified that the scattering goes like that. So now, it was thought for maybe 10 years that, I don't know if it was 10 years actually, I know. Certainly the Gelman-Low stuff was 1954. It was, and then Kalin-Zemancic was 1970. It was, I don't know, a few years after that, Gross and Wilczek at Princeton and Sidney Coleman and Politzer at Harvard noticed or applied the Kalin-Zemancic equation to Yang-Mills theory, and in particular to SU3. And what they found was that the beta function was negative. These beta functions were all positive in the lambda 5 or G5, the 5-4 theory, and in quantum electrodynamics, the beta functions are positive. Here, the beta function is negative, and you have mu dg mu d mu, which of course is beta of g mu. This is just notation. It is minus 11g mu cubed over 16 pi squared. So there's a minus sign. This is in this is just 3 colors, 1 species of quark. And if you now do this same business, you just perform this same integration, but now you have this minus sign and these slightly different coefficients instead of I don't know, 12 pi squared, you have 11. Well, I forget what the difference of the arithmetic is. Anyway, if you do it, what you find out is that in quantum electrodynamics, quantum chromodynamics, the simplest version, you get that it looks like this. 1 plus 11 gm squared over 8 pi squared log E over m. And so what do you see here? What you see then is that because the beta function is positive, as E increases, this denominator gets bigger. There's no minus sign that would give you a 0. Instead, the thing gets bigger. But it gets bigger slowly because it's a log effect. But of course, this other one got bigger slowly also. The denominator here got smaller, but slowly because it was also a logarithm. And so what happens is the coupling constant gets smaller as the energy gets bigger. And so now, of course, this was the lowest order calculation, and it was for the case of just one species of quark, say red up quarks, and nothing else. And, so let me erase the board and go to the whiteboard and see if maybe I'll leave the course advertisement on the board. Take out everything else. So now we can go to, well, I'll show you what the result is for 2 loops, and it's probably 2 loops with arbitrary numbers of, not arbitrary numbers of quarks. If you have too many flavors of quarks, the quarks, it turns out, change, they move the beta function in the wrong way. They move it so that the effect that we see in the non-repeating case goes down. And so let's see. So this effect, namely that the strong interactions get weaker at high energy, people call this asymptotic freedom. And then people said, well, what about at low energies? Well, of course, the trouble is that at low energies, the coupling constant gets bigger, and so perturbation theory fails, and so you really can't say very much from at least perturbation theory. But the belief is that the coupling constant gets sufficiently strong that that explains why quarks and gluons are fine. So let's see which one of these is actually works. Are there any questions? I think something in the tone of my voice today suppressed questions. Anyway, let me show you what it looks like. The coupling strain, this is alpha strong at energy 0.22, 0.1, and energy is going, let us say from, it looks like 10 JeV to 150 JeV. And the one loop formula is doing essentially that. The three loop formula does basically that. On the other hand, if you, well, one could do the same business for SUN gauge theory with NF flavors of quarks. Then this beta function, beta of G mu, is minus. The minus means you're going to have asymptotic freedom. G cubed mu over 4 pi squared, 11n over 12. So this one is the one loop. This is one loop. This is 3 loops actually. And then there's minus n sub f over 6. So if you have too many quark flavors, in other words, what do we have? We have up, down, charm, strange, and top, bottom. We have 6 of them. So we get a -1. But on the other hand, this is 33 over 12, so this is 3. So this is 3 minus 1, 2. So the thing is comfortably negative. But on the other hand, if NF is, so you have asymptotic freedom if the number of quark flavors is less than 11 times the n of SUN divided by 2. And, but of course, as far as we know, n is 3. And NF at the moment is 6. Another way of thinking about this is to redefine this m squared as lambda squared times an exponential. And if you choose the exponential as 16 pi squared over 11 minus 2 NF over 3, all that times Gm squared, and that's in the exponential. You make that definition, you then get that alpha S of E, so the strong coupling constant of energy E, by which we mean G squared of E over 4 pi, and again, natural units, is 12 pi over 33 minus 2 number of flavors of quarks log E squared over lambda squared. And so now this thing, lambda here, if you ask, well, what's a reasonable value for lambda? 230 MeV is a very plausible value of this. Let me just see what is. Okay, so this change here where you see what's happened here is that on the right-hand side, you no longer have a dimensionless coupling constant. Instead, you've got an energy scale, lambda. Sidney Coleman called that dimensional transmutation. I don't know really why he did that, but it caught on and everyone talked about things like that. Let me just describe the renormalization group now in lattice gauge theory. There, what we've got as a cutoff is, of course, the lattice spacing A. And once you put in a lattice spacing, finite lattice spacing, all the infinities are gone, but they reappear in the calculation as you let A go to 0. And so what do? You typically got a coupling constant then, and what you know is that you have to adjust the coupling constant as a function of the lattice spacing in such a way as to make sure that the physical parameters that you're computing remain constant as A goes to 0. And so what you want is the physical thing that you're computing, which is a function of A and G of A, dA, you want that to be 0. And of course, you want that to be 0. Well, of course, it's really in the limit of A going to 0. Anyway, what is that? Well, this is that equation. You can rewrite it as dA d log A dP dA. In other words, you can rewrite that as A dP dA, and this is then equal to dA d log A times dP dA, and this is the same thing as dP d log A, and you want that to be 0, and what you then get is 0 is, and there are two terms, partial log A the lattice spacing, plus partial G of A, partial log A, partial G of P equals 0. So it's the same idea that you just want the physical parameters to be independent of the scale of, in this case, the lattice spacing. And the lattice beta function then is minus dg d log A, and well, in the notes I've written down what they are in lattice gauge theory, and computing them is a long story. Let me just show you what happens if you do the integration. You get something that's kind of interesting mathematically. Well, it's just sort of interesting, since it is mathematics. When I say mathematics, I mean mathematics on the north side of Lomas. Okay, I'm not talking about mathematics that people in the math department talk about. If you do this, what you find is that the dependence of the lattice spacing on the coupling constant, after you do Sidney Coleman's trick of dimensional transmutation. Well, let's see, did I skip too much? Yeah, I skipped too much. Okay, let me write it in two forms. So the lattice spacing as function of the coupling constant is a constant times these things from the beta function, beta 0 plus beta 1 g squared over g squared, and it's raised to the power of beta 1 over 2 beta 0 squared. These are numbers, beta 0, beta 1, they're just constants. e to the minus 1 over 2 beta 0 g squared, okay? That's what's really interesting. That's an essential singularity. So in other words, the lattice spacing goes to 0, as g squared goes to 0, as the lattice, I'm sorry, as the coupling constant goes to 0, the lattice spacing goes to 0 incredibly fast. It's an essential singularity. It's e to the minus 1 over g squared. So that is fast. Equivalently, in terms of lambda, it is beta 0 g squared to a power minus beta 1 over 2 beta 0 squared. This probably is an approximation. E to the minus 1 over 2 beta 0 g squared. Well, it's essentially the same formula. It's just a different definition of lambda. Another way of thinking of it is, how does g look as a function of a, and it's approximately 1 over a big square root, and the square root is beta 0 log 1 over a squared lambda squared plus 1 over beta 0 log of 1 over a squared lambda squared. All that to the 1/2. Okay, and so here the coupling constant goes to 0 as a goes to 0, but it does so logarithmically because then it's a log of 1 over essentially 0, which is large. But that's a logarithmic approach, so it's slow. We've only got a few minutes left today. Let me now get to the basic idea of the renormalization group in condensed matter. In condensed matter, one is integrating over, let us say, fields, but these could be arrays of spins and so forth. I think the whole business is much simpler if you speak in terms of fields. And these fields are written as e to the I. We can write them as in Fourier space this way. d kd is essentially 3. But this is a cutoff. I don't know whether that's a U or a cut off. This is a cutoff at the lattice spacing, because in condensed matter we actually are talking about solids or liquids with with a real cutoff. That is to say, if we are describing the system by a field, the fluctuations can't be smaller than the distance between atoms or molecules. And we might be describing these things in terms of a Hamiltonian, and typically there'd be a grad phi squared, and then other terms, g2 phi squared plus g3 phi cubed plus g4 phi to the 4th plus ... and all this ddx. This is a theory of fields in space, not space-time, and d is typically 3, but you could do 2 dimensions if you want. And what you're talking about, of course, is the beta function, which is an integral e to the minus beta h of phi, path integral d phi. Now, the essential idea, which was originated by Fisher, Kosterlitz, Kadanoff, Wilson, and others, was to say, let's consider a stretched field, which is an overall coupling constant change and then we change the thing by, change x by x over L. And so this is, if you just substitute into this formula, you've got A sub L integral, same cutoff lambda, e to the I k dot x over L, same phi of k. I'm just going to call it d cubed k. Well, all right, let's do dd k, right, but the same lambda and A sub L, and the L is there. Okay. Now, what you do, the next thing you do is you say, well, how does A of L, how do we choose A of L? Well, we have to choose A of L so that this term here is invariant under the scaling. And then after we've figured out how A of L behaves as L changes, we're going to have to figure out how each of these G's goes, because all of them involve the phi. So if we look at the derivative term, it looks like this. It's a partial of phi L, partial x, I'll just call it x, it can be x, y, z, whatever, dd of x. And so this is going to be a sub L squared, because there's an A sub L, where the hell is it here? And then this is going to be the derivative of phi of now x over L, partial x squared integrated ddx. And now we do a trick. We say, well, we're going to write this, rewrite this, and this is actually, it's one simple idea. We're going to rewrite this as integral, still partial phi of x over L, but now we're going to write this as L partial x over L. And this thing is squared, and then we have still d dx, and now we make one more change, and we have this. We're going to put, well, I'm going to do this right now. I'm going to put in L to the d here and L to the d there. Okay. And so what we've got now all together is L to the d minus 2, A sub L squared, and everything else we can just call x prime. And so we call that partial phi L of x prime, partial x prime squared dd of x prime. We want that to be invariant, so this thing has to remain constant. In other words, we say that A sub L has to go as L to the 2 minus d over 2. And if it does, then this thing is constant. I'll put the notes online. The next thing is, well, how do you keep these terms constant? And we're essentially out of time, so let me just use the blackboard to write down what the answer is. The answer then is that G sub n of L has to go like this. L to the d plus n 2 minus d over 2 times the ordinary G sub n. And so then what we say is, if this exponent, if d plus n 2 minus d over 2 is greater than 0, what does that mean? That means that the coupling constant grows when you change the scale. And such things are such couplings, so we say then that Gn is relevant. That means that as you look at the system, on macroscopic scales, the nth coupling constant becomes really important. If, on the other hand, this thing is 0, we say Gn, so d greater than 0 relevant, d equals 0 marginal, and d less than 0, what do we call it? Irrelevant, well, obviously. And so that's how one can characterize the different coupling constants in condensed matter from the point of view of the renormalization group. Of course, there's been a lot done with the renormalization group, and what the best articles are on this subject, I'm not really sure, but this is very important in condensed matter physics. And in particular, these techniques of the renormalization group have been used to study critical phenomena, scaling, phase transitions, and so forth. And this is the modern way of dealing with, or of analyzing these questions. In 524, I guess I can do a little more of the condensed matter stuff, but I have not worked in condensed matter apart from biophysics, so I can't really. I'm going to have to learn it a week ahead of you guys if I do that. But the plan in 524 is to certainly do more about renormalization and more about the renormalization group, and then more about a whole lot of other subjects in quantum field theory. Aren't there any questions? I mean, I've got all this candy here to reward questions. All right, is anybody hungry? Let's say it's the end of the hour, and if anybody's hungry, I'll throw up candy.